This will be the next chapter in the 2 chapters for exam 4, which will start on November 14th. I'll do a review prior to that, but this is on chapter 11, Oscillations and Waves, and this is also the basis for lab 10 for the simple pendulum. We look at oscillations there. All right, so when we look at waves, all right, easiest thing is a spring, a vibrating spring. This a spring oscillates back and forth with a period. So if I take one, you can look at it anytime. It oscillates back and forth. Or a pendulum swings back and forth, and you have the lab. So it has a period. The period is time for it to take one full trip back. So that's 1, 2, 3, and so on. And for a oscillating spring, the time for it to come back to this highest point each time is the period. So we had, again, with the spring, and this is what we're going to be dealing with, and the pendulum, much like back in chapter 6, we talked about the kinetic energy and potential energy of gravity. We had the spring and we had the pendulum. One is based on force of a spring, the other is force of gravity. So back on the spring, one at a time. Remember, for a spring, so to exert it, much like a scale has, if it takes 1 pound to move it down 1 centimeter, then 2 pounds will take it down 2 centimeters. 2 centimeters, 3 pounds would be 3 centimeters, and so on. And if we write the graph of extension, so X versus force or weight, you're going to have a graph like this, which is linear with, the force is linear with the distance exerted, and this force is given by minus kx, where this is the spring constant. For this example, I use pounds, but it's normally in newtons per meter, force per length. So that's the spring constant. The higher the spring constant, more force it takes to exert at a certain distance. So that's section 11.1 as far as that's concerned. And a couple other things here on 11.1, while we're at it, is as it oscillates, it has a period, t in second, that's related to the reciprocal of the frequency, which is in hertz, and this is in seconds. We've talked about that before as far as the basic concepts there. So that's the part there. As far as that's concerned. When we talk about the size, when it oscillates, when it oscillates, the amplitude is how big it is oscillating. Right, so the amplitude is how much it moves away, above or below the equilibrium point. So the amplitude is the size of that. We'll get into that. All right. Also then, we talked about potential energy. Remember, for gravity, it's just mgh. For a spring, it's 1/2 kx squared, which we talked about in chapter 6. So k is the spring constant, x is how far it is pulled from its equilibrium point. So that's the potential energy in joules, but that's not the primary focus. There's a little bit on chapter 11 too, and as we so now chapter 6, we talked about potential energy, conserved energy, total energy is oscillates between kinetic and potential back and forth. So that was part of chapter 6. Now we're going to be looking more at the motion of the system as it oscillates. So let's see here. Oh. So when we have a spring, right, and we talked about this a bit, right, the force is K minus Kx, and or Kx, and so that's the spring constant K. So when we have an oscillating spring, the period, if we actually look at the graph of this, and so if we have a spring that oscillates, it'll oscillate in a pattern like this, which is the classic sine wave. So this is a sine wave. Based on sines and cosines, and this will be the x. This is time. So if we actually were to track a spring going up and down, it would oscillate up, down, as we track in time, measuring this in time. This is the amplitude, right? A is amplitude. This time from here to here is the period from one point to another point, either crest, either that to that, crest to crest, trough to trough is the period, and then the frequency, as we said, is 1 over the period. So if I'm standing here and waves are coming by me, it's like how many waves per second are coming at me. Now for a spring, the period, as we mentioned, is given by 2 pi square root of m over k, where m is the mass that's hanging here, k is the spring constant, 2 pi, we know what that is. So this is the period. As you can see, the heavier the mass, the longer it's going to take for it to move up and down. Likewise, the lighter it is, the less the K is, the longer the period's going to be. So that's the relationship of that. And again, the frequency is 1 over the period. All right, this is part of section 11.3 in the text as far as that's concerned. So I'll leave that up for a minute. And then go from there. Okay. So I should say, you notice that this period has nothing to do with the amplitude. If I was to take a spring and oscillate just a little bit, just like the pendulum we did, the amplitude has nothing to do with how long it takes for the period. If I pull way down, it's actually going to just go faster. The period will still be the same. It only depends on the mass, and it only depends on the spring constant. It has nothing to do with the amplitude. So if I was to pull it down a little bit, we'd see something like this. It would only have a smaller amplitude, but the period and the frequency would still be the same. All the differences here is this has a smaller amplitude, as far as that's concerned. One other thing here, we get the frequency, angular frequency, which we talked about a while back, chapter 8 on angular motion, is given by 2 pi times the frequency, where this is in radians per second. So we're talking about radians per second, which sometimes you need. That's the case there. Okay. All right. I'm now going to move on a little bit. Let this hang here. And then move on now to the pendulum. Okay? Pendulum has the same kind of sine wave, so I'll keep this up. Relationship between period and frequency is the same, but there's an interesting picture in the book of pendulum, and talk a little about Galileo and how he sort of had this understanding that a pendulum would actually be a very good clock, because what he noticed in church as the little things were swinging and the light fixtures were hanging down, you know, they had these big cathedrals, so that things, and sometimes they'd be swaying back and forth from whatever wind came in or something. And he noticed that the period stayed the same even if the oscillations became smaller and smaller. And you know, well, that's really clever. I mean, that would make a very good clock, is what he realized. Because trying to measure time has always been difficult. I talked about that a little bit beginning of the semester, is measuring time. How do you do that? I mean, we did that, you know, you measure, look at the path of the sun over the course of the day, but how do you actually get more detail in that? Again, the concept of time flowing came from having time clocks based on dripping water. Or you have an hourglass with sand and you can measure time that way. But that is only for short periods or certain things like that. Anyway, for a pendulum. So pendulum, you have a mass hanging at the end. It has a length L, has an angle. So the amplitude would basically be the size of this case. So either a large amplitude, maybe way out here, a small amplitude would be oscillating back and forth here. So the period is the time it takes for it to go one, come back, one, and so on. So for a pendulum, the period for a pendulum is given by almost exactly like the spring, except it's L over G. I should probably use the same L. The textbook uses little l. So L with G for Earth, G is 9.80 meters per second squared. So it only depends on the length, and it only depends on acceleration of gravity of where you are. So you go to somewhere on the moon's 1/6. So a period is going to be, a pendulum on the moon is going to be much slower. Right? Again, as doesn't matter on the amplitude, and it has nothing to do with the mass in this case, unlike the spring, which directly depends on the mass. So that's a period for a pendulum. And this is section 11.4. All right. So there isn't a whole lot to do with this concepts in this chapter. So that's 11.4. We're not going to do anything on damp motion. We're not going to do anything on resonance, even though that has interesting concepts. We talk lab 11 on standing waves on a string, and lab 12 talks about resonance. And there's a couple things here. They talk about 11.6, but we're not going to do that. One example is the Tacoma Narrows Bridge disaster, and I'll post a link to a video of that crashed in November 7, 1940, and the famous Loma Linda earthquake of October 1989, which was famous. Fortunately, occurred during the World Series between the San Francisco Giants and the LA Dodgers. Not the LA Dodgers, can't be right. Oakland, yeah, the city's there. San Francisco Giants and the Oakland Athletics. And I was actually watching the game at the time when all of a sudden Al Michaels came on because the TV started vibrating, and then the picture disappeared. He said, we're having an earthquake. And as a part of that, this long bridge called the 880, which was a double span bridge. The top span, because of this wave sent through, crashed, killed approximately 50 people. So that's the only earthquake I've ever seen live occur. So but we're not going to cover anything like that, but it is an interesting topic, and it is sort of how we do 11 and 12 as far as that. All right, so moving on here, we'll get into more on 11.7 I'll talk about next, but I'll be dealing with more of that as far as velocity, waves, and such in chapter 12 is concerned, because we'll be doing sound waves. So this is the pendulum, and let me move on to chapter 11 then, section 11.7 and 11.8 more or less together. All right, so when we talk about waves, we have a wave that is moving down. This could be a water wave as such. We'll see sound waves. Waves, if it's a water wave, it has a particular speed, and that's given by the frequency times the wavelength. So the wavelength of the wave. So the frequency is how fast the waves are come by a given point. So it's water waves. You sit there and count how many come by every second, like 1, 2, 3, 4. So if it's 10, 10 in 1 second, then it's the wavelength. If we're actually measuring this in distance, the wavelength is how far the waves are physically separated by each other. So the wavelength is the distance waves physically are apart. So this is the wavelength in meters, and this is the frequency in hertz, and the product of the two is the speed. Now we're going to see water wave, light wave, electromagnetic. They have a particular normal speed, so if you increase the frequency, the wavelength is going to get less. But we'll talk more about this in detail, chapter 12 on sound waves, and later on next semester, if you've taken 11.02 on electromagnetic waves. So that's what we're doing there. But when we have waves, we have two types of waves, and we have, all right, and the best way to do this is just take the book and show it to you. If I take a spring, because I can't see and never demonstrate very well, and oscillate it back, like up and down, like swing it up and down, you get a transverse wave. The spring goes up and down, or slinky goes up and down, the wave goes that way. On the other hand, if I just pull it a little bit and give it a jerk, a wave going back and forth in the same direction is propagating. That's what we call a compression wave. So the top one is a transverse wave, the bottom is a compression or longitudinal wave. So those are the kind of waves you have there. So we have transverse, all right? It's perpendicular to wave propagation, meaning where's the wave going, and longitudinal, or compression waves, I'll call them, is parallel. So parallel to wave propagation. All right. So, well, let's see what other kind of waves. Yeah. Actually, there's a whole lot in there. Yeah. And then, concerning types of waves, right. Yeah, I'm not going to get into energy. Let's see. The only other section I would do, yeah. All right, since we're on it here, two other sections I'll cover is (1111), superposition, and basically what this means is if I take let's say a rope and put a wave, like kick it this way, and then the other direction I kick a wave downward, so these two waves, one is coming at each other this way, and the other one will be if I do two, one's coming this way and the other's coming that way, both together. And this is like, again, a rope or something where it exerts, you just take a taut rope, flip it a bit so a wave goes propagating down. In this case, when they meet together, what will happen is you'll see this occurring, and then afterwards what will happen, so this will be right when they meet, and then afterwards what you'll see is the bottom wave will go like that, and the top wave will do that. They'll actually act like they never saw each other. They just go right through each other. That's the thing about waves. Now if I see two that are the same direction, right, these will actually add together, and then afterwards they'll look the same, but one will be going that way and the other will be going this way, right? What we call here, when they cancel out at this point, first cancel out, we'll get into this a lot when we do sound and light. This is what we call destructive interference. Meaning they cancel each other out. And then the bottom one is when they're two and they add together. This is constructive interference. Okay, so destructive interference, they cancel each other out. Constructive interference, they add together. And that's all we're going to be doing there is a conceptual basis of that. All right. All right, again, more of that, I'll be dealing with more of this when we get to sound. All right, the last thing here, and is standing waves, and this will be the basic. We saw this, or if you haven't done Lab 11 yet, or looked at what I did, standing waves occur when you have we have resonance, and if we have a wire or string of a certain length and we vibrate it at the right frequency, we will get standing waves occurring. This is called resonance. In this case, here we have 1, 2, 3, we call antinodes. Antinodes are the peaks, nodes are so. Right? So this will be section 11.7. section 1112. So resonance, this is lab 11 and 12. We'll see 11 and 12 will be a little easier to actually visualize. 11 and 12, I kind of showed you how it worked. So what we have here is we have a string and we have it fixed at both points and we somehow vibrate it. Right, it'll vibrate up and down. This is the lowest, it's called the fundamental frequency. Never sure if I get that spelled right, fundamental. Anyway, all right. Frequency, then the next one, so this has n equals 1, so it has one antinode. We don't count the nodes at the bottom ends. This is n equals 2, so we got an antinode, this is n equals 2, one node in the middle, n equals 3, node, antinode, vibrating in the middle. So you got two nodes, this is n equals 3. So, that's what we're going to have there. Chapter 12, the lab 11 and lab 12 will get into this much more detail when we talk about sound waves. In chapter 12, we'll get into much more detail of this. So this we call standing wave. Again, it's if I have a string and we're able to excite it with a certain frequency, like either a vibrator or if it's a wire, something to get it to resonate, you'll get a so-called standing wave. So this is n equals 1, n equals 2, 3, 4, and so on. So that is chapter 11. There isn't a whole lot to it as far as that's concerned. Most of it's qualitative. There's a little bit of quantitative as it relates to frequency, period, for pendulum and spring. I'll talk more about that to review for exam 4.